in some sense, it's very boring because things you have seen before and so on. On the other hand, there are certain things that we have to make clear from the beginning. So that's what I'm going to tell you about. The upshot of this. This is how commutative law and associative law are usually stated. But to us, that's not so important. What's important is that we're going to skip that derivation. These two laws, as stated, leads to the following fact, right? So the consequence of, I won't write it down, right? The consequence of the commutative and associative laws of addition leads to the following fact, which we call theorem, which is the statement that given a finite connection, numbers, they can be added together in any order, and the result will be the same. Any number. So for example, right? So you have calculator, right? So at some point I'm going to have to help, right? So I see your calculator, I'm going to use large numbers. 37 plus 59 plus 81, 42 plus 95. 5 numbers. What's your pleasure? What do you want to add first? It's up to you. Doesn't matter. So suppose I feel like doing the last 2 things first. I would say, now this is really kind of mind-boggling. I do that first. And then suddenly feel like adding the first one. Right? But then I say, I change my mind. I do this first. And then I put in 59. Right? In one moment, I feel like doing this. Another moment, I said, no. One and first and the last first. So 37 plus 95. So in fact, I like 95 plus 37. Right. Then I add to 81. But then I like this total addition very much. So I add to it the other 2 numbers, which are actually what?
42 and 59.
So that's one example of adding those 5 numbers anywhere you feel like. Now you all say, of course they're the same. Right? I really want someone to do it. Okay, you count. Right?
Yeah.
Okay, you do this one first. This one, 42 plus 95 is 42. 137, and then 37 plus 81. 128? 118. Okay, so 59. Right? Then it's understood. You like it. And this, just add that.
255.
255. That's 59, right?
Mm-hmm.
And at the end, what you get?
214.
Okay, now try this. What did it? 9 plus 37 is what?
132.
132 plus 81. What's this? Oh, this 42 is 59.
Is it 51?
101. And then This is 2 what?
213.
And then 3.
214?
Okay, yeah, the same. Now, look at the numbers. Do you see any of them repeating? No, no. 137, 118, 59. This is what? 213, 101. Or this, 101. See, look at this. Completely unrelated. But the end result is still the same. Yeah, so then, I hope you're impressed. It's not obvious. It's not obvious. So I mean, you should explain this to your kids. It's not obvious. Yeah.
But if you had lengths, these lengths in front of you,
Yes.
right? And you mixed them all up and you gave them to the kids and you said, what is the length? They're all going to, no matter what order they're going to be in, they're all going to be the same length.
Yes. But that's another way of looking at it. You see? Things should be looked at more than one way, right?
Mhm.
So, of course, you look at this geometrically as you just say, well, this is all these 5 things in front of you, concatenated already.
Yeah.
You just switch the order and
Right.
it's all the same. That's one way. But look at it as pure numbers. It's not obvious at all.
No.
So when you want to impress them, you don't do the obvious thing, but do the not obvious thing and you impress. Because there's a psychological battle you want to win. Because they all, like you sitting here now, look at this and say, oh, I know, and then you see through it. But these are really quite non-trivial things. You want them to have a different perception of some entire old things. So this is the upshot, not the derivation from the statement of the associative law and the commutative law to here is extremely boring. And you don't want to do it. But you should know that's exactly what happens. From those boring statements, you get this astounding fact. That's now in the end of the chapter, you actually see one particular case with 5 numbers. I think you actually go through the motions and show why that works. But that's enough. You leave this to professionals. Now, for multiplication, of course, is exactly the same statement. Multiplication is also commutative and associative. And the upshot is exactly the same statement. They can be multiplied together. They can be, actually, I don't know, multiplied together in any which order, and the result will be the same. Same statement. And that's what we're going to use in our computation. To us, there are certain things I want you to know inside out, line by line, word for word, and syllable by syllable. Those are the important things in school mathematics. There are certain things such as these. Yes, you can afford the time and the energy, you should do it. But basically, it's not particularly enlightening. It's better that you just use it and forget it, because you don't learn much from it. You know as how it is, right? You want to watch grass grow? They do grow, but you don't want to watch it. There's certain things like that. It's not particularly educational, so we don't spend time on it. We want to concentrate on things that really matter. And this matters in some level. Professional mathematicians worry a lot about such things. But for us, it just let it pass. Now, let's look at the this one. This one, the addition one. I want you to take 10 seconds anyway. It's not worth more than one time for that. Do you think it's useful in real life?
Mm-hmm.
Give an example. Oh yeah, you read the book essentially.
No.
Oh.
You've said many, many, many.
Oh, I see. Okay, you explain to us. Explain to us, right?
Shopping if you're checking out at the cashier line.
They are all using this theorem. Your cashier register. Right? You buy a lot of articles. If the amount of money you pay depends on the order in which those are run up,
Yeah.
you're in a lot of trouble. So close your eyes and let them do it any which way they want, because it's everything. So these are things that you don't think about, but they have real consequences. Huh? Okay. Now this is all this leading up to. Now these are, of course, as I said, these are facts you use all the time, and most likely you use them even without thinking. So I'm not adding that much more to your knowledge, other than to clarify for you the structure that. Knowing this, well, you want to know this. All you have to know is those two simple statements: n plus n equal to n plus m, and then n plus n plus p is the same as n plus p. Just know it, because one day you might want to not use it. But however, so these are sort of boilerplate, standard routine. The next one is a distributive law, and that's not routine. And in fact, lots of students, maybe even among some of you, have difficulty with that theorem, with that law. What that says, well, you all know the statement. What some may have trouble with is not the statement itself, but being able to use it. So, the distributive law. What it says is that for any three numbers, M and L, hold on. Want to multiply this way? Well, we can also do it this way. All right, since multiplication is commutative, right? This is the same as saying what? N plus L. That's the same statement, is it? Excuse me, right? Commutative. Now, this is how the distributive law is always stated. There's really not much choice, because it does tell you how to distribute this. You see, you have two things there, you distribute this, together. No problem. The main problem is that, well, equality means what? The two are the same, right? That is, you see this, you recognize this. But it also means if you see this, you should recognize this.
Yeah.
But that's what most of you get. Right? And that's what you need a lot of practice on. So whenever there's an equality, you always have to say it's one way, but then it's the other way. And this part is probably harder to detect. And so, well, actually there's nothing to talk about other than to put into practice.